Hey guys, here's another problem that I wanted to spend some time on real quick. We have this dam, the Grand Coulee Dam located in Washington State, which has the following power output. It's our job to figure out how many cubic meters of water per second have to flow through it in order to generate that amount of power. It's not a terribly hard problem, but some of the ways I've seen people solve this are just ridiculously overcomplex. I think that there's a faster and easier way to do this that only requires a single equation. It's good practice for doing algebra on units too. Let me show you what I mean. Here's a single cubic meter of water that's located at the top of the dam. The only forces acting on it in the vertical direction are its weight and the normal force. These are equal and opposite in magnitude since the water doesn't change height as it flows to the side, and we can ignore any horizontal forces that are responsible for pushing the water in that direction. Once that cubic meter of water flows over the edge, there's no longer any normal force. So the weight of the water is going to pull it down and act on it during the 170-meter fall. This is just 1 cubic meter of water, though. We need to account for this happening multiple times every second. Here's how we can do this. Let's call the total number of cubic meters of water flowing through the dam every second x. If we want to relate this to the total amount of energy that the dam generates, we'll need to incorporate the conversion factor that says a cubic meter of water is equal to 1,000 kilograms. We saw that the force doing work on the water is its weight, which is mg. The mass part is included in our conversion factor that we added here. So we'll have to multiply this by the acceleration due to gravity to properly count the weight of all the water that's flowing through each second. That force acts entirely during the fall, so let's multiply it by the 170-meter height of the dam. Also, we can't forget that only 92% of that work is converted to energy, and that can be written as a decimal, like this. This entire product on the left is what's equal to the energy generated by the dam. Let's even convert the watts units to joules per second, since we'll have to play around with those units in the next couple steps. This is the only equation that we'll need to solve the problem. Let's take everything on the left-hand side here and multiply it together. You should end up with the following, and I'll go through the process of unit cancellation just so that we're all on the same page. Since we have meters cubed below, we can eliminate the meters squared upstairs, and that will leave us with a single meter unit in the denominator. Following that cancellation, our left-hand side units have the following form. Let's also convert this joules unit to its definition, which is kilogram meters squared per second squared. We can roll this extra factor of seconds that we're dividing by into a single unit ratio, like this. With all that simplified, the plan is to isolate x on the left-hand side, which should result in units of meters cubed per second, if we've done things correctly. We have kilograms in the numerator above as well as the numerator below, so both of those can be eliminated. We also have seconds in the denominator above and below, which means we can eliminate some of those too. In the end, 2 portions of seconds are removed from the denominator above, and the seconds squared in the lower denominator just go away. Let's clean this up a little bit before moving on. Here's what's left. If we divide meters squared by seconds, and then divide that by 1 over meters, well, that will add a factor of meters into our top unit ratio, which will turn it into meters cubed per second, just like we wanted. If we divide this remaining numerical ratio on our calculator, you should get a number pretty close to this one. Remember though, we used some values with 2 significant figures along the way. That means we'll have to cut this down to 1300, or written in scientific notation to make it look nice, 1.3 times 10 to the third cubic meters per second. And we're done. No extra equations necessary. That's all for now. Take care, everyone.